Okay, but here's the cool thing about 2's complement numbers. Given two numbers in 2's complement form, and to add them, I'll just do ordinary binary addition. So say, for example, I wanted to add negative 10 plus negative 3. Negative 10 would be negative 16 plus 6. And for negative 3, so I can use method 1 to calculate this one as an example. I have 3 in binary. I invert all the bits, add 1, and this gives me negative 3. But I'm going to need an additional bit padded at the front. And so this is called sign extension. I can add an additional 1, and I still have negative 3. Okay, so with these two signed numbers in 2's complement form, and I want to add them together, I'm just going to do normal binary addition. So 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, carry a 1, so forth. And I'll drop the carry so I get the following, 1, 0, 0, 1, 1. Well, let's check the result. So this is negative 16 plus 3 is negative 13, and that checks out. And this will work whether the numbers are both positive, both negative, or positive and negative. What if I also wanted to subtract y from x? The way we can do this is just to compute negative y and then just add negative y to x. So if I wanted to subtract 3 from 10, I'm simply going to add negative 3, which we calculated above, to 10. And I get 7, which also checks out. Okay, now when doing arithmetic, we'll want to be careful with what we call overflow, which basically means when we add or subtract numbers together and our result can't fit in the number of bits that we have for our sum. For signed binary numbers, I can also have overflow, and I have to be a little more careful. So as an example, say I was adding 13 to 13, and I have these represented with 5 bits. So I add positive 13 to positive 13, and I get the following. But notice that this is incorrect. This is a negative number. Same thing is true if I subtract 13 from negative 13 or add negative 13 to negative 13. Something's wrong again because I just added two negative numbers and I'm getting positive 6. So this actually leads us to then coming up with a scheme to tell us when we have overflow. And the intuition is that if I add two positives and get a negative, then I have overflow. Or if I add two negatives and get a positive, then I also have overflow. So this is a good way to remember when I have overflow. When implementing it in a circuit, though, there's actually a simple implementation for checking overflow, and that is that I can just look at the last two carries. And if those last two carries differ, then I know that I have overflow, or that it's not a valid 2's complement number. So to see this, we can write out all the possibilities. So first, let's say we're adding two numbers, and the first number a is larger than 0, and the second number is also positive. So I add all the bits together, and I'll just look at the two most significant bits here. If the carry into that last position is a 0, then my result's going to be a 0, and I'll also have a 0 on the output, and this will be okay. But if I have a carry in to that last column being a 1, then the result is a 1, and the last carry out's a 0. So the last two carries differ. I've just added two positive numbers and got a negative, so I know that I have an overflow. Now what if one number is positive and one number is negative? So if I get a 0 into the carry for the last column, I'm going to have a 1 and a 0 output. That's okay. If the carry into the last column is a 1, then the result is 0, and I get a 1 out, and that's actually okay. And this is in fact a rule which you can check on your own. Whenever I add a positive and a negative number in 2's complement representation, I'm never going to have overflow. And then the third possibility, when I'm adding two negative numbers, so if that last carry is a 0, then my result is a 0, and I have a carry out of 1. Well, adding two negative numbers gave me a positive number, and the last two carries are different, so I see that actually this is an overflow. But if that last carry in was a 1, then my result is a 1, and my last carry out is a 1, and I don't have overflow. So to summarize, an easy way to remember when you have overflow with 2's complement arithmetic is when you have two positive numbers and you add those together and you get a negative, that obviously can happen, so that's going to be an overflow case. And when you add two negatives and you get a positive, that's the other case. And those are actually the only two cases where you're going to see overflow. You can never get overflow if you add a positive and a negative number. And then finally, a simple implementation with an adder can just XOR the last two carries, and if those differ, I can also tell that there's an overflow.